Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over the June 2019 Algebra 1 New York Regents exam, problems 1 to 4. This is going to be a detailed coverage of how to do each problem. If you need something quicker, just go ahead and visit our website. And don't forget to subscribe to our channel to get updates to the remainder of this review series. Alright, let's take a look at question number 1. In question number 1, we're being assessed on how to factor higher degree binomials. In this case, we're looking at a quartic binomial. The question is, the expression w to the fourth minus 36 is equivalent to. So the task is to factor this quartic binomial and see which of these factored states is equivalent to it. Before we get started with the factorization process, let's go ahead and review the formula that will guide the factoring process. So let's go over the formula. The formula that we are going to use is known as the difference of squares formula. Okay, difference of squares. Alright, so you might have seen this formula before being applied to lower degree binomials. You might have seen this formula: a square minus b square. Remember, you have to have a difference, a square minus b square. Now, if you want to factor this, all you do is you take the square roots of the first term and the last term, and you express the roots as a sum and difference. Okay, so if you square a square, you get a. If you square b square, you get b. So it's going to be a plus b times a minus b. Remember, when you're taking the square root or rooting, you're dividing the power by 2. Okay, that's basically what it is. Now we can extend this formula to any binomial, difference of binomials where the powers are even and the same. Check this out. What if we have a to the fourth minus b to the fourth? All we'll do is we square root these terms and express them as a sum and a difference. So if I square the first term, I get a square. If I square the second term, I get b square. So a square plus b square times a square minus b square. Let's extend it further. How about a to the sixth minus b to the sixth? This is a square also. How do we know that it is a square? Any even power term is a square. Why? A square is a term where the power is divisible by 2. Okay, so when we square these two, what we're going to be doing in essence is dividing their powers by 2. So we're going to have a to the third plus b to the third times a to the third minus b to the third. Alrighty? Okay, now let's go ahead and attack the problem, having written down the formulas that will guide our problem solving process. So what we're trying to do here is we are trying to factor w to the fourth minus 36. Now take a look at these three formulas right here. Which one do you think is applicable to this particular problem? It's the middle one, right? Because that's the situation where the first term is raised to the fourth power. Now what we're going to do, we're going to apply the difference of squares formula. We're just going to square root the first term, square root the last term, and express the roots as a sum and a difference. Now to make sure no one is lost in this process, let me pull out the terms and find their square roots independently. Okay, so if you have w to the fourth, we have, let me put the formulas on top here. We need, this is, what we have here is a to the fourth minus b to the fourth. Okay, so just like this. Now we want to figure out what is a square and what is b square, so we write them as sum and differences. Okay, alright, so we have the first term is the a, right? So a to the fourth is w to the fourth. So to get what a is, we just simply root both sides, take the square root, and that will yield the result a square. Remember, when you root, you divide them by the power by 2. A square is going to be w square. Okay, so that's the result of rooting w to the fourth. And then we also have, what else do we have? We have 36, b to the fourth. So b to the fourth is 36, right? So b to the fourth is 36. Now what are we going to do here? We're going to square root, right? Using the difference of squares formula, we have to root the first and the last terms, root. So the square root of b to the fourth is just b, and is b squared, and the square root of 36 is 6. Now we're going to express this factored state as the sum and the difference of a squared and b squared. You notice what we have here. We have a squared plus b squared, and then a squared minus b squared. That is going to be the factored state. All right. So using that formula here, let's see what we'll have. Our final answer is going to be w squared, which is a squared plus b squared. B squared is 6 times a squared again, which is w squared, minus b squared. B squared is 6 again. Ladies and gentlemen, this is the equivalent form of the expression w to the fourth minus 36. Alright, so the answer to question number 1 is option 4. So now you know how to do it. Let's go ahead and just verify to see if our selected answer is correct. Okay, you don't have to do this, but some individuals do not like to factor. So another way to do this problem is by expanding the options to see which one yields w to the fourth minus 36. So we're just going to pick the answer we selected because we know for certainty that this should work. Alright, so this is just to check to show that our selection is in fact correct. So what I'm going to do is I'm going to expand this, and if I end up with the original problem, the original expression, then I know that my answer is in fact correct. We're multiplying two binomials, so we're going to double distribute. Just FOIL it out. First, outer, inner, last, just like a Punnett squares. Alright, so what do we have here? W squared times w squared is w to the fourth. Remember, when you're multiplying exponents with the same base, you add the powers. Okay, w squared times negative 6 is negative 6w squared. 6 times w squared, so we've done first outer. Now we're doing inner, is plus 6w squared. And then last, plus 6 times minus 6. When you multiply different signs, you always end up with negative, so negative 36. Now if you take a look at the center terms, they're opposites of each other, so they take each other out. And then our expanded form of this result we got here is w to the fourth. Let's try that again. W to the fourth minus 36. Now, is this answer the same as what we started with? It certainly is. So that shows for a certainty that our answer is correct. So what do you all think about this factorization problem? Do you think it was easy, medium, or difficult? Let us know by posting your response to this question in the comment section below. Okay? Alright, let's take a look at the second question, question number 2. In question 2, we're going to be assessed on how to evaluate functions at a specific value, and we will be implementing the order of operations in the process. So the solution is as follows. We have the function f of x equals 4x plus 5. We're asked to find the value of f of negative 3. What on earth is that? What is f of negative 3? Well, we just look at what f of x is, and that will tell us what f of negative 3 is, right? So f of x is a rule. What this function does is it multiplies the input by 4 and adds 5 to it. As simple as that. So whatever the input is, you just multiply by 4 and add 5. Now let's set it up here. We're going to have 4 parentheses negative 3 times, close that, plus 5. Alright, did you notice what I did here? I replaced my x's with parentheses first before substituting the input value. Alright, this is something that is very, very important. When you're evaluating functions as indicated in our caution here, you always want to use parentheses because it helps you avoid mistakes. So do you agree or not with this advice to use parentheses when you're substituting? Let us know if you think parentheses are important, or let us know if you think that parentheses are not important, and tell us why. Okay, so now we're going to use our order of operations. What is that? Please excuse my dear Aunt Sally. Parentheses first, exponents, you multiply, divide from left to right, and then you add and subtract from left to right. We have multiplication and addition here. So what we're going to do is multiply first, all right? So 4 times negative 3 is going to yield negative 12. Negative 12 plus 5. Negative 12 plus 5 is negative 7. Remember, when the signs are different, you subtract and keep the sign of the bigger. All right, so the answer to question number 2 is option number 2. All right, now let me show you a neat little trick. Since you can use a calculator for this test, let me show you how you can use your calculator to evaluate functions right from the home screen. There are 2 other ways that you can go about this process, but I'll just show you the first one. Alright, so I'm going to show you this neat little trick using the TI-83 Plus calculator. Alright, so first thing we're going to do is we're going to store the input value. Okay, the input value we will store in the variable x. And then after we store the input value in the variable x, we will evaluate what this expression is. Alright, so let's store the input value. The input value is negative 3, so negative 3. STO means store in x. Press enter. How do you know if it's stored? Just press X, enter, and then you see negative 3 is outputted as the constant that has been assigned to this variable. Now we'll just type up this expression, just the right side, 4x plus 5. And then when you press enter, the calculator will insert negative 3 in the x position and calculate it and give us a final answer, which is negative 7. So this is just one out of two other ways in which you can evaluate functions using the TI-83 Plus calculator. So which do you prefer? Doing this problem by hand or using a calculator? Well, I would like to know. Just post your opinion in the comment section below. Okay. Alright, let's take a look at question 3. In question 3, we're given 4 relations here: a table, a graph, an equation, and a map. The question is, which relation is not a function? So in this problem, we're being assessed on our ability to identify what a function is and what a function is not. So depending on the presentation that you're given, that will determine the approach that you will use to ascertain if a relation is a function or not. Okay. All right. The first one, we have a table. Whenever you're given a table of values, what you are looking for is repetition in the x's. Okay. So let's write that down. Repetition in the x's. If there are no repetition in the x's, then it is a function. If there are any repetition in the x's, then that's not a function. Okay, so let's just be more specific. No repetitions in the x's. All right, so look at all the x's. Are there any repetitions? There are no repetitions in the x's. So what does that tell us? This relation is a function. Why is it a function? If there are no repetitions in the x's, that means that every input is being assigned to a maximum of 1 output. Okay, if you have one input going to more than 1 output, which results in a repetition in the x's, that relation is not a function. Okay, so in this problem we're looking for what is not. So what is should be eliminated. Number 1 is gone. Okay, number 3, we have a graph. Whenever you're given a graph, you're looking for a graph that any graph that passes the vertical line test, the VLT. Okay, vertical line test. So does this graph pass the vertical line test? Well, let's see. All we just have to do is draw a vertical line and sweep it across the entire domain and see if we have an intersection that's more than 1. So If I draw a vertical line and sweep it past the entire domain, we can see that all the intersections are exactly 1. And since this is an absolute value function, we expect the same pattern to repeat itself forever. Alright? So since the maximum number of intersections is 1 for every point in the domain of this function, what does that tell us? It tells us that this relation right here is the graph of a function. So it basically passes the vertical line test. Okay, so let me highlight my vertical line. So we have one there. There's another one. So just to illustrate, what I'm trying to show you here is that these vertical lines are intersecting the graph at exactly 1 point. All the vertical lines do that. Okay, so what this is showing us visually is that every input which go along from the vertical line from the x to the graph is assigned to exactly 1 output. Alright, so this passes the vertical line test. What does that mean? It means that this relation is a function. Now let me show you an example of a graph that fails the vertical line test. Let's say you have something like this. Do you see why this fails the vertical line test? This relation is not the graph of a function, because if I draw a vertical line right here, what do you have? You have 3 intersections. So this is good, but we have another intersection and another intersection. What this is telling us is that one input will be assigned to 3 different outputs, which is not what a function is. So this fails the vertical line test. Hence, it is not a function. Okay, this one is a little bit abstract, but hopefully you get the gist. So fails the VLT, not a function. Alright, this is just a side example. Now, let's shift our gears to option 2. Option 2, we have an equation. Now, whenever you're given an algebraic equation or a function and you're asked if it's a function or not, all you do is you look at the powers of your dependent variable, namely the y's. Okay. Now, in this particular case, this y has a power of 1. If the power of the y is odd, then it is a function. If the power of the y is even or absolute value, or you have absolute value around the y, then it is not a function. Okay, so let's write down our observation. Y has an odd power, which is good, and no absolute value brackets. Okay, if it had an even power or an absolute value bracket, one of the two, then it is not a function. So since y has an odd power, no absolute value brackets, that means it is a function. That's a pass. Okay. All right. Let me show you an example of functions that are not absolute, that are not relations in equation form that are not functions. For example, you have y to the 100 plus x equals 4. This is not a function because the power of y is even. Or if you have x equals the absolute value of y plus 3, let me write that again. X equals the absolute value of y plus 3. This is not a function because the y, the dependent variable, has an absolute value. And then this is not a function because the y has an even exponent. Okay, so these two are not functions. But this is a function because the power of y is 1, and 1 is what? Odd. Okay. All right. Number 4. We have a map here. So this one is a little bit complicated to do. You could visualize it, but if you just take a look at what's going on, you want to ask yourself, is every input going to a maximum of 1 output? That's what you're asking. 1 is going to exactly A, which is good. 2 is going to A and B, which is horrific. That is a no-no. So since this 2 is going to 2 outputs, that automatically tells you that this relation is not a function. Alright, another way to approach this is just to use your mappings, convert it to ordered pairs. Okay, so here we have 1 goes to A, and then 2 goes to A, and then 2 again goes to B, and then 3 goes to C. So if you look at your ordered pairs here, you see that we have a repetition in the x's, and that's a violation of a condition to be a function. All right, so let's write down what we observe here. The input 2 is assigned to more than one output. Is assigned to more than one, it doesn't matter if it's 2, 3, 4, 5, 6, it's automatically not a function. Okay, so more than one output, and that tells us that it is not a function. Hence, this is the correct answer that we're looking for. All right, the other ones are functions, so we don't want to select them. Answer to question number 3 is option number 4. Now, out of these 4 options, which one is the easiest for you? Which relation is the easiest for you to ascertain if it is a function or not? We'd like to know. So let us know what your selection is. Put it in the comment section below and tell us why is that particular representation the easiest for you to determine if a relation is a function. Okay. Alrighty, let's take a look at question number 4. In question 4, we're being assessed on transformation of functions, quadratics to be specific in this particular case. The question reads, given f of x equals the quantity x minus 2 squared plus 4, g of x equals the quantity x minus 5 squared plus 4. Question. When compared to the graph of f of x, the graph of g of x is... So what kind of shifts? We see that all 4 options are talking about shifts. What kind of shift is going on here? Now, the easiest way to do this problem is just to graph both of them on a graphing calculator and then compare them to see what kind of shifts is going on. But I'm going to show you how to approach this problem algebraically, and then we will go over the graphical approach in solving this problem. All right. So, in order to do this algebraically, you need to know what the rules are for shifts of functions. Okay, so let's go ahead and do a real quick review on how to shift functions. All right, so first one, if you have, let's make this a little bit thinner. That's good enough. A function composed with x minus h. Okay. If you have a number that's been subtracted from the x in the parentheses, this, ladies and gentlemen, is a shift. H units. Now, this is tricky. Whenever it's grouped with the x, the sign does the opposite. So x minus h means you're going to shift h units to the right. Okay. If you have f of x, now the number is being added to the x in the parentheses. This is going to be a shift. H units where? To the left. Alright, so when a number is grouped with the x, adding or subtracting means a shift to the left or right. Okay. Now, if you have a function and you're adding a number on the outside, bam. In this case, it's going to be a shift vertically. This is going to be a shift k units. Guess what? Up. So the vertical shifts make sense, but the horizontal shifts are kind of backwards. All right, so just keep that in mind. It's a little bit tricky there. So if you have a function minus k, this is going to be a shift k units down. All right, we have all the formulas that you need for the Regents exam at our website, mathgotserved.com. So if you want to review your formulas for the Regents exam, do visit our page, and then you can print out the formula sheet for your consideration. Alrighty. Now let's go ahead and attack the problem. F of x equals the quantity x squared. The quantity x minus 2 squared plus 4. Now this is where we are starting from. We're going from this function to this function right here. X minus 5 squared plus 4. So the question is, what alteration was applied to f of x to go to g of x. Now, if you look at the number on the outside, the k's are the same, plus 4 plus 4. So the difference is not a vertical shift up or down. Okay? But if you take a look on the inside, you notice this is minus 2 and this is minus 5. So how do you go from minus 2 to minus 5? Think about it. If you owe $2, how do you go up to owing $5? Do you save or spend? You spend more, right? So in order to go from minus 2 to minus 5, you minus 3. Okay? So we're minusing 3 from the x. That's what's going on here. Let me illustrate that to you algebraically. This is really nice. So you have g of x equals x minus 2 minus 3. So we are subtracting a number from the x inside the parenthesis, plus 4. So whenever you subtract a number from the inside, you're looking at case 1 or 2. In this case, when it's minus, it's going to be a shift to the right. If it's a plus, it's to the left. So since it's a minus 3, this implies that the graph of g, the graph of g, yes, is shifted 3 units to the right of h. No, of f. Right of f. Okay? So that's basically what's going on here. Alright, so this is the algebraic approach for solving the problem. Now let's show what it looks like graphically. Alright, so we're just going to graph both of them. The first one is quantity x minus 2 square plus 4. Okay, let's graph that first. So we see where this graph is. This graph is shifted 2 units to the right. So let's see what the other one is going to look like. I'm going to make it the thick one, okay, so it looks different. So make the second graph thicker. So the second graph is g of x. So it's quantity x minus 5, quantity square plus 4. Let's see if we have a shift 3 units to the right. Okay, so let's graph it. Bam. And you can clearly see what's going on here. The 2, this is the first one and this is the second one, and it's a shift 1, 2, 1, 2, 3. 3 units to the right in order to go from this to this right here. Okay, let me just zoom in a little bit more so that you can see what I'm talking about. So I'm going to use my zoom box feature. So what we're looking at is we're comparing the vertices. Okay, so if you just focus your attention on the vertices, you can basically determine what kind of transformations are happening on the graphs. Alright, so I just want us to focus our attention on the vertices here. Observe what's going on. So that's the first one, and that's the second one, and you can see the shifts. It's 3 units to the right. Okay. Alright, so I did a snapshot of the graph so you can see exactly what's going on here. So this is the first vertex right here. Okay, this is the start and this is the final. And then what's happening is you go 1, 2, 3. 3 units to the right in order to go from the first one. This one right here is f of x. This one right here. And then the darker one is g of x. So we can clearly see, ladies and gentlemen, that the answer is option number 2, shifted 3 units to the right. So in this problem we can see that we could do this problem by hand or with a calculator. So that leads us to the question, if you can do this particular problem with a calculator, does it mean that it is not necessary to know how to do a problem like this algebraically by hand without a calculator? Well, we'd like to know what you think about that question. Just post your response in the comment section below if it is necessary to know how to do transformations by hand without a calculator. Alrighty, now let's take a look at question number 5. In question 5, we're being assessed on how to write polynomials in standard form. Now, how do you know if a polynomial is written in standard form? Let's go ahead and describe or explain what it is to have a polynomial in standard form. Okay, so a polynomial polynomial is in standard form when the terms are arranged or ordered by the size of their degrees greatest to smallest. Okay? So if we order the terms of a polynomial by the size of their degrees from the greatest to the smallest, now that polynomial is going to be in standard form after the arrangement. Okay? So we have 6. Let's go ahead and take a look at this polynomial that we have right here. It's a 7th degree polynomial with 4 terms. So it's 6x to the 5th plus 8x minus 3x to the 3rd plus 7x to the 7th. So what we're going to do is we're just going to take a look at the size of the degree of each term. Alright? And then the biggest one is the one that's going to come first. And then we're going to go down in order. Alright, so let's take a look at all of them right here. Which one is the term with the biggest degree? That's going to be first. So look, what do I mean by degree? Well, this is a degree. This is 5. This has no degree, has an invisible degree, which is 1. And this is 3. And this is 7. So the biggest one is this one right here. So this will be the first term. And then we have 5, 1, 3. Which one is the next? Going from biggest to smallest. This will be the second term. Okay. And then this will be the third term. And this guy right here will be the fourth term. Alrighty. So let's go ahead and write this polynomial in standard form. So the term with the biggest degree comes first. It's going to be 7x to the 7th power. Next one is the 5th degree term plus 6x to the 5th. The next is the 3rd degree term minus, you take the sign, 3x to the 3rd. And then the last term is the term with the smallest power, which is the 1st degree term, 8x. So this is the polynomial written in standard form. So the question is, which is correct? Out of these 4 options that we have right here, which is the correct one? Is it Ann, Bob, Carrie, or Dylan? So if you look at it, we can clearly see, let's see, make sure. Oh, this is clearly the right one. Ann is the correct student response. Alright, so this is basically how you write polynomials in standard form. Thanks so much for taking the time to watch this presentation. Really appreciate it. Let us know what you think about this presentation. If it was helpful to you in your review preparation for the Regents exam, to give us a thumbs up. Your positive feedback is very valuable to us. You can post your questions or comments in the comment section below, and we'll be more than glad to respond. We upload videos to our page on a daily basis, so do subscribe to our channel so you can get notification of updates to our uploads. A ton of support resources, including the transcripts to this video, can be found at our website, mathgotserved.com, under New York Regents. Thanks again for watching and have a wonderful day. Goodbye.